All right. Thank you for coming to class the day after the midterm. I appreciate that. There's a big stack of handouts up here, which means that lots of people aren't here. But thank you for coming to the day after the midterm. We're doing new stuff today, completely new stuff. In fact, if you program for a long time, you may never have even gone to this level before in any of your programming, prior programming experience. So it's kind of fun, and we're going to spend the next 4 lectures on it. So it's pretty important stuff. Did anybody get a little bit annoyed with that little red exclamation point on their exam last night? Sorry about that. We're trying to fix that, so next time it won't be quite so trigger happy to say, you cheated, we're saying you cheated. We don't think any of you cheated, so, but thank you for being honest to people who came out and said, I got the red thing, I didn't do anything. So sorry about that. The TAs have started grading, well, we've started grading the exam already, and it is going all right. We'll see how it turns out. I will have results before the end of the weekend. So we'll shoot some results your way before that. I wanted to start out today by showing you something. I'm just going to show it, and then I'm going to discuss it for 1 second. Some people know what I'm going to show here, but I just want to show this. It's 1 minute long, and you may or may not have seen this. But take a look. Okay, so what you have just witnessed is SpaceX last week, which is kind of a private version of NASA. They send rockets into the air. They actually sent a Tesla car into space from this on this rocket, so it's like shooting through space, kind of as a publicity stunt because Elon Musk runs Tesla and he also runs SpaceX, so he did that. But what you just saw, and I'm going to pause it on the coolest part. Let's see, right about maybe here. There we go. Okay, so well, it's not even quite. You can't even see both of them. There we go. Okay, what's happening here is 2 rockets are independently landing 20 feet apart, upright on a platform. Now, if that doesn't get you excited for engineering and computer science, like you know how much programming went into doing that? Like it's an immense amount, millions of lines of code went into like getting that to work. And of course, they did it lots of times and it crashed and whatever, but that was like so exciting from an engineering perspective to me because we've never done something like that, and it just means that like we're really getting good at this sort of stuff, so it's exciting, and it's hopefully kind of like, you know, hey, if the stuff we're doing in class today, or not just today, but in general, like it might not be quite as sexy as you might think some other things. That is sexy, right? Like that is really cool. Seeing like rockets do that and like completely programmed is amazing. You heard the crowds, they went nuts and whatever, and I think that's really cool. So just wanted to start with that and say, if you're not motivated by some of the things you do, trust me, you can eventually do cool stuff like that, and wow, that's really exciting. So, all right. Let us start talking today about x86-64 assembly language. We are actually going to start learning a new programming language in some sense. Okay, so we're going to learn the language that your programs get compiled into. Now, these are your C++ programs and your C programs, and they're kind of your Java and JavaScript and all those programs. Java actually compiles into another intermediate level that then further gets compiled into the assembly language for your specific computer. Okay, Java was actually designed to write once and run anywhere. In other words, you can write it on one platform and hopefully run it on any other platform, and it's pretty good the way it works. But what's happening, what we're going to get into today is like we are really going under the hood to start looking at the binary representation. Well, we're going to look a little bit at the binary, but the textual representation of the machine instructions that actually run on your computer. Okay, some of it may surprise you about how simple it is. Like things are getting kind of compiled down to a level where everything is explicit, right? There are no more for loops where things just kind of counters update automatically and this and that. Like if you want to update a counter, there's an instruction which has to update the counter, and there's an instruction which has to move memory from one location to the other, and there's an instruction that has to jump to the next some other line in the program. It's very, very explicit. It's also kind of detailed. So there's a lot to it, and in fact, the assembly language that runs on your Intel-based processors is kind of old when it comes down to it. 1970s is when they designed the language, basically. And they've kept this backwards compatibility for all the way until now. And so some of the things we look at now, we say, oh, maybe this could be done a little bit better. There are other processors where things are done differently. Okay, there's the processor that's in your phone, which is most likely an ARM processor. That's got a completely different instruction set. But if you went and learned that, you'd find out that, oh, it's really not that much different. There's just actually fewer things to remember, and fewer things are a little more regular. Okay, so the reader has a big section on assembly language that's not quite done yet. I'm going to kind of do it like before each lecture, as it turns out. So this weekend I'll be doing the lecture for Monday, and I'll make sure everything's in there. But I think I've kind of gotten it to a point where the reader has the knowledge you need to know. Okay. The other thing that has the knowledge you need to know is this one-page handout that's up here if you haven't gotten it. And on the back is some other stuff. So this page is the one that we will give you for the final exam. So you don't have to memorize anything on this page, although you really do know how to use the stuff on this page. Okay? So that's that. All right, what is this assembly code that we're talking about? Sometimes we call it assembly code, sometimes we call it assembly language. All computers have an underlying language that the hardware understands. Okay, that's called machine code, and it's the code that your C program that can run more or less on any computer as long as it has a compiler that will do it. But it gets compiled down to this machine code that only runs on that specific computer. It used to be that all computers had was machine code. We're talking like 1950s, 60s sort of thing. And if you wanted a program for one type of computer, you had to learn the assembly language for that computer. And as we'll find out, it's a pretty verbose language. Okay? There are no niceties involved in this. Okay? Machine code is what handles the lowest level operations, not quite the lowest level. Go take a EE class, you'll learn even lower level stuff. But pretty much the lowest level things on your computer. And it's things like networking happens there, memory management. Like you think malloc, like how does malloc actually get the memory out of the computer? It's from these underlying instructions. Okay? Reading and writing to your disk, reading and writing to memory in general. And all those things are happening at the machine code level. Okay? Assembly code is a text-based representation of those underlying instructions. The instructions, by the way, are just ones and zeros, like everything else on your computer. But we have a nice textual representation that says, do this, and it does one little thing at a time, like each instruction, maybe two. And we'll talk about those details. So that's what assembly code is. And as I said, your compiler, GCC, creates the assembly code. We're going to see an example of that in a few minutes. Assembly is really raw. One of the reasons that we talk about void star pointers and generic functions and all that is not really to like annoy you by these crazy void star things. It's to start getting you used to this idea that there's really no type when you get down to a lower level. Types go away, and assembly language is very raw. The compiler needs to know about types and things, but the assembly language itself, there is no notion of type. There's integers and floating point numbers. That's about it at the assembly language level. Okay? Humans can write assembly language. You probably don't really want to. It kind of makes your eyes bleed after a while after you write a whole bunch of it. You really want to be able to read it, though, just in case you need to dig in a little deeper than your program. As it turns out, last quarter we actually had the class write just a very small amount of assembly. This quarter we're not going to. We're not going to have you actually write any, which is fine. It's not the biggest deal to actually do it. You certainly could write some, but it used to be you had to. Nowadays, GCC does a really good job and probably makes better assembly code than you could by doing optimizations and so forth. Okay, so that's what assembly code is. As I said, the code that we use is based on x86 assembly. It's still called x86-64 for the 64-bit word size that we have. But it was created in the 1970s by Intel for their processor called the x86, the 8086, which was their first like 16-bit processor. That's interesting. It was 16, now we're at 64. And Intel has said, look, we want pretty much any program that you run today, well, sorry, any program you created in 1978 to still run on your computer today. It's called being backwards compatible. So they've kept up all of these instructions. And some of the things that we're going to learn about today and going forward, you got to kind of remember why, the fact that they were built in 1978 or designed in 1978, and some things have changed. So some of the register naming, that's the stuff on the back of this sheet, that when you look at that, some of the register naming is based on that old model, and they've just extended it. So it gets a little bit tricky sometimes, because you're like, wait, I thought a word was 8 bytes or whatever, and stuff, but now you're telling me it's, or I thought a word was 64, and you're telling me it's 8, and we'll get to what all those things are, or 16. So there are some historical roots to this that you got to kind of bear with us on, okay? We made the choice to teach you x86 assembly because it's what you use every day, and it's the computers we use every day. If you go and process a Raspberry Pi, or go and program on a Raspberry Pi or an Arduino, not going to be the same assembly code. In fact, an easier assembly code, in my opinion. Okay, so there have been some things that we have hidden from you so far. Okay, we've talked about high-level languages. We've started to dig down into like bytes and started to dig down into little endian and that sort of thing. But we still have hidden a bunch of things that we're going to have to kind of open up and show you now. Okay, machine code is based on what we call an ISA, or an instruction set architecture. Okay, that defines the behavior of the system. Okay, the ISA has all of these specific things involved in it that we're going to have to learn a little bit about. So we're going to take that and go with it. Behavior is defined as if instructions are run one after another. Well, that's nice, because that's like our normal programs. One instruction, then the next, then the next. Okay, and memory appears as a large byte array. Oh, that's good, because we've been starting to think about large byte arrays. Okay, so again, we prepared you to get to this point, but now we get to learn the details. Okay, so let's talk about some of the things that have been hidden from us. Okay, well, the first thing that's been hidden is there's this thing called the program counter, PC, also known as %RIP, and not like RIP like ghost sort of RIP, but %RIP, which stands for the instruction pointer. Okay, the program counter and the instruction pointer. That is a place in memory that says, where's the address of the next thing you're going to do? That's all, or kind of the current thing you're doing, as it turns out. But it's basically something that's there. So in other words, there's something inside your computer that says, what's the next thing I'm going to do? And it's listed, and the address is put in that little thing called RIP. We'll get to there in a bit. You can't go and modify that directly, as it turns out. There's ways to do it indirectly, though. There is this thing called a register file. So far, we've been talking about memory, and we've said all memory has an address, and all memory is a big, long array. There are these things called registers, which, in fact, on our system, there's 16 of them. In fact, they're listed right here for you on the back of this sheet. Okay, we'll get to the details of that in a few minutes. And those 16 registers are able to hold 64 bits each. Like, in other words, one long is able to be held in those registers. The interesting thing about the registers are, number one, they're the fastest memory on your computer. Registers are super duper fast, way faster, hundreds and thousands of times faster than your memory system, as it turns out. Why? Because they're built directly onto the processor chip, and that's how they make it really fast. Okay, they're really fast. There's only 16 of them, but everything the processor does uses those 16 registers, which means that your program, you will see those registers a lot in every piece of code that you write or read in assembly. Okay, we'll get to what those actually do in a minute. Okay, registers a lot of times hold memory addresses. They're just pointers. Other times they actually just hold data, like integer data. Okay, they'll hold a number that you want to multiply by some other number. They'll hold a number that you want to subtract, or they'll hold a number that whatever number you've got, they will hold. Maybe it's an index into an array, but that's what's going to be inside this register. They also hold your program arguments in many cases. So when you pass arguments into a function, guess what? They get put into these registers. Why? Because they're fast and everything's going to use those. We will see a zillion examples of these things. Okay, there we go. I said registers, they're used for arithmetic, they're used for local variables are stored in registers. I kind of lied to you that local variables are stored in the stack. These days, most are just stored in registers because often you don't have enough, or you have enough registers to hold all your local variables. You might as well put them in the fastest memory possible. Okay, so that's that. Okay, we also have our other set of registers which holds what we call condition status. And they hold status information about something that happened. So for instance, if you add two numbers together and the answer is 0, there's a register that says, hey, the last thing you did resulted in 0. That's kind of neat. Why is that useful? Because if you're trying to do like if-else sort of things, what you want to do is maybe check, oh, did I just do something, did I just get to the end of my loop? Yeah, if I subtract the total things that I had from the ones that I've gone through, that'll become 0, and that's some condition that happens. So that's another type of register. Okay, those are listed on the bottom here. They're actually not real registers. They're called condition codes on this sheet. Okay, we will get to all that. This is just kind of an overview right now. Okay, there are also vector registers. These are ones that hold your floating point values and your big integers and things like that. We're not going to concentrate on those in here. You're not going to have to know anything about the floating point registers or the other vector registers. Just know there's other sets of registers that you could get more information on if you want. Okay? All right. Unlike C, no types. Types are gone. So we don't have, now we've just got a whole bunch of bytes in memory that we have to access. That's what memory is to an assembly language program. Makes it a little harder to keep track of things sometimes, but that's why we're not handwriting these things. Okay? There is no distinction between unsigned and signed integers. What? There's no distinction. In other words, a register is a register is a register. It holds a number. That number has a bunch of bits in it. That's it. When you want to do things and consider a number in 2's complement or a number that's negative or a number that's whatever, you have to actually, as the compiler, figure that out and go, okay, now I need to do an arithmetic shift because this number to me is signed and so forth. Okay. There's no difference between pointers. Every pointer in assembly language is a void star pointer. Yuck. Okay, so that's important. A single instruction. We're going to talk about lots of instructions. In fact, if you look at the common instructions on your sheet, it's on the left-hand side. Move SBL, move ZBL, LEA, add, sub, IMUL, neg. All those are some of the instructions that we will start to use. You don't need to know more than the ones on this page, but you need to know them, the ones on this page. Okay? You don't have to memorize them because I'm going to give you this, but you need to know how they work. And those instructions do like basically one thing. Okay? A couple of them do two things, and we'll talk about when that happens. But they basically do one thing. If you use the move instruction and you say move from here to here, that's all it does. It moves one byte or one 16 or 64-bit word from one location to the other. That's it. Notice there's no for loop instructions or anything like that. It's like one little thing for each instruction. Okay? Here's your example. There's an instruction to add two numbers. That's what it does. When you say add some register and another register, that's what it does. Okay, so we're dumbing things down in that sense to the sense where we say, okay, look, we're telling the computer add two numbers, that's all we're doing. None of this like variables and all that. I mean, it's all registers and it's all like one thing at a time. Okay? I talked about this. There's already instruction that transfers data between a register and memory. That's another thing that we'll learn how to do. There's an instruction that conditionally branches. What does that mean? It means that based on one of those status flags or status registers, it will go to a different part in the program. That's how you do if and else statements in assembly. You've got an instruction that says, if a status flag is such and such, go to this location. Otherwise, just go to the next line. That's all it does. Very simple stuff in that case. Okay? One C statement will often generate many assembly language instructions. Why? Because our C instructions are more like compact. They actually do more things. So when you have when you set an integer into some value, it's probably doing a couple different things at once, right? Those are the instructions that are happening at once. Okay. All right, all of that talking, let's actually look at some of this assembly code. Okay? All right, first things first. Here's our C program. Okay, it's a pretty simple C program. We set a register, or we set a variable I equal to 1. We print hello world, and then we're going to print that register, or that, I keep saying register, it's on my brain now. We print that variable, and then we return 0. Okay? Well, when you compile it, and if we went into, in fact, I'll show you this. If we, let's do it this way. If we go here, and I'm going to copy this line here, just so I get it right. Okay, if we go into Myth, and in lecture 10, there's a hello program, and if I, forgot the no $sign at the beginning. There we go. If we say GCC dash uppercase S, and then the rest of our compile line, what it does is it says, oh, okay, all you want is the assembly language that I'm creating, because GCC does that. And if we go and look at that, .hello.s, it's this file, that little hello program like created this big file here. Okay? Let me show you what it looks like with all this other stuff stripped out, because I don't think you don't need some of this stuff to understand. Some of it's for the computer to like put things in the right location. But here's what it comes down to. Okay, let's take a look at some of these things. All right, we have a string in here called hello world. Well, the first thing in the assembly language program it does is it says, look, I'm going to have a string called hello world. Okay, that's going to happen before the program ever like gets going. That's going to be immediately put into memory and as part of the program. Then it says this weird thing where it says SUBQ. That means subtract. We'll get to what Q means in a few minutes. And then it says subtract 8, that's the $8, from this. That is one of your registers that we're going to talk about in a few minutes too. Okay? SP stands for the stack pointer. We definitely have to deal with the stack here. We'll see why it does that at some point, not necessarily today. Okay? And then we're doing a bunch of moving. We're moving 1 into some other register. Okay? We're moving this .lc0, that's actually a label. That's where the string lives. We're moving the string into some other register, that address. We're just moving addresses around right now. We've moved 1, and we moved an address. Then we're going to move another 0, as it turns out, into some other register. We'll get to what all this is. I don't expect you to understand any of this quite yet. Don't worry. Okay? And then it finally calls printf, which means that all of this was set up for printf. Okay, so that's what's happening. Then it says, okay, finally, move 0 into this register. By the way, it moved it into it up here, too. You'd think it would have left it there, but it can't do that. We'll find out why later. And then it adds back to this stack pointer, and then it does this RET, which is just return. All of that came from this little program right here. Okay, all of those little things. But do you see how, as I walked through that, you're doing one thing at a time. You're moving 1 into something. You're moving an address here. You're moving that. That's what's happening in this code. Okay? I don't expect you to understand that yet. Shag.
So honestly, one of these assembly functions seems to be that the source is the first parameter while the destination is the second. If that was the case, then why did the makers of C decide to revert that to the string library?
Yeah, good question. Very good question. So Shaggy says, look, if you look at this, all the assembly languages have this source coming before the destination, but then all our string libraries have the destination coming first. Well, one of the reasons is that we are showing you one version of assembly. You can actually have the compiler create a whole different version which has it in the reverse order. So maybe they were using that reverse order when they came up with it. That's probably what it is. But yeah, you have to remember which one it is. In this case, it's always source into destination for the ones we're doing. Good question. OK. That's for your first kind of assembly language program. We will get you, by the end of next week, you will understand this. You'll be like, oh yeah, I got this, no problem at all. OK? Just like learning a whole new language. And it really is learning a whole new language. If we make that program and run it in GDB, in fact, I've still got it up here, OK, we can go and if we just make it, OK, sorry, that's all the other programs too. What we can do is we can open this up, GDB, hello. OK, now normally you can list the program. You've already done that, right? But you can also disassemble the main function. So if you type DISAS for disassemble main, take a look what happens. It has all your instructions there. That's been totally hidden up until now. Like, for a good reason. Did you ever need to know that? No, you didn't need to know that yet. But now you're going to have to start knowing that, right? What these numbers over here are, this is the address of the actual instruction. This is the address of the next instruction. This is the address of the next instruction, et cetera. This is the actual instruction itself. Okay? And in fact, if we went and looked at this, 0x40054F. If I go down here and say, oops, wrong one. There we go. There we go. If I say print, let's see. Or how about this? How about I do, yeah, let's do, I'm trying to think of what's the easiest way to do this. Let's do x, no, let's do print. We'll do print. We'll cast it. Everything's a void star pointer, or a void star pointer, so we have to cast this. We print char star, and we print 0x4005F4. Let me see if I got that right. Aha. At that location lives our hello string. So there's an address right there. Remember how we moved that like label? That's what's going on here. We're right here. We are moving an address of hello into this register. We'll get to all those details in a minute. Question? Do the addresses correspond to the program counter number? Yes, they do. Yep. So as you're running the program counter will have that address in it as you go through the program. Good question. Anybody else? All right. So we can look at some of these things. Again, this is all just kind of overview of this stuff right now. Okay. You can also do this in kind of a split mode. If you type, let's see, what is it here? Layout split. If you're in here and you type layout split, it will actually give you both the C code and the assembly code next to each other. I don't really like this mode because it's harder. It sometimes crashes. It doesn't always work right, and it's just kind of annoying to use. I normally don't do that mode, as it turns out. So anyway, now we're starting to see the kind of thing we're going to be up against as we go along. Okay? So what do we take away from this little thing I showed you? Well, first of all, one C statement can lead to multiple assembly language instructions. Move is pretty common. Look at how many moves we have. Move, 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 move. A whole bunch of moves. Moves are super duper common. We're moving memory addresses. We're moving things back and forth into registers all the time. I think something like 70 or 80% of instructions are move instructions. Like there's a lot. We're always moving data around. It's like the biggest thing we do. Setting up a function call. It's not just like, hey, call the function. You have to do a whole bunch of setup. Remember, all this was setup for that function call. Okay, so that's not particularly nice in some cases. Okay, what else do we have? We've got the stack. Something's going on with this. Ooh, that's not good. This always seems to happen when I do this, and I never know why. But anyway, so we've got the stack here. Something's going on with that, and then return values. Well, we returned 0 here, okay? Turns out that we always return values into RAX. Okay, we always return values into RAX. Well, we'll find out why that's the case later. I'm going to try that. Hang on. Let me see if I can just get this back to normal here. Maybe I'll, oops, hang on. Pen, nope. Let me try this again. There we go. Okay, pen. Oh, all right. We'll see. We'll see how long it takes before it screws up again. Okay, so that's the first thing that we have to take away, all those things. Lots of stuff going on with these assembly language programs. Okay, So let's dig into some of the details here. Because the 8086 processor was a 16-bit processor, a word means 16 bits. You've got to get used to that, because these days we think of word and we say, oh, it's a 64-bit. Word means 16 bits. Okay? 32 bits are words that are double words which use L for long. Ah, that's not long. Long is 64 bits. Well, not now. Okay? L means 32 bits. 64 bits is a quad because it's 4 times the 16-bit word. It's 4 times bigger. That's 64 bits. Okay? Here's how that breaks down. Here's how that breaks down for your different C types. A char is a byte, right? We know that by now. The code would be B, and it's 1 byte. Great. A short is a word because it's 2 bytes and it's W. An int is a double word, which is kind of a long. I know it's terrible that we have to think about this. And it's 4 bytes. A long is 8, which is Q for quad. You'll see these and you'll start getting very used to them, et cetera, et cetera. A char star pointer is also a quad word because it's 8 bytes. A float, remember there's single precision and double precision. Single precision floats are 4 bytes, doubles are 8s. Okay? Pointers are 8 bytes, we already know that, and the suffixes are going to be important very, very soon. Okay. Here's where we get into the registers. As I said, there are 16 of them. They're on the back of this page for you. They are what we call general purpose registers, meaning that they can store pretty much any 64-bit number for any reason. There are some limitations in there, but for the most part you can think of, okay, they're going to store data in 64-bit chunks. Okay? The names begin with R, okay? Like register, as in register, right? They didn't used to. They used to just be, used to be only like 7 or 8 of them. It used to be AX, BX, CX, DX, get a pattern? Yeah. SI, that's not the pattern. And DI, that's also not the pattern. BP, which stood for base pointer, not important anymore as it turns out. And SP, which is the stack pointer. These are general purpose registers. It's kind of like having your program have int A, B, C, and D. It's like, well, I'm just going to have these names, so they named them A, B, and C, and D. That's what that's all about. Okay? Each register had a particular purpose that can be reused to some extent. When 32-bit computers came along, they extended these. E for extended, I think it's extended. EAX means the 32-bit version of AX. EBX means the 32-bit version of BX, because BX is 16, EBX is 32. And as I'll show you in a second, EBX contains BX. It's just extending, and it's like the extra parts of that. You'll see in a minute how that pans out. Okay? When 64-bit came along, we had to change the names again, or we had to update the names. Now they're called RAX, I think for register, and then RBX and so forth. And EAX is contained in RBX, which also contains BX. I know it's like, you're like, what's going on here? It'll become clear in a second. Okay? All right, on the back of your sheet, you've got the same page I'm about to show you. Okay? All of these registers have what we call nesting behavior. Okay, so take a look at this. The originals were AX, BX, CX, etc. Okay? Once we got 32-bit registers, well, now they're bigger, and we call them EAX and EBX. But EAX is this amount, and AX is this amount. By the way, there's also an AL, which is the 1-byte version of AX. It stands for low. There's also an AH, which I'm not going to make you know. Okay, I know this is all like, whoa, there's a lot going on here. It's all right, we'll get to what it all means. But this is the idea. When we got to 64-bit, we had RAX, which is this whole thing all the way across to there. Okay, so there's 16 of these things. Okay, they have different purposes, general purposes. They can be used for other things. We always return things in AX if we can, RAX. We always, we generally use BX when we say that the caller owns this. That will become apparent when we start talking about functions. Okay? We also pass arguments sometimes by, well, most of the time, by registers. Okay, so for instance, we've got di down here is the first argument. Si, or rsi, or rdi, the second argument. Rsi is the second argument. Remember we saw that a few minutes ago. Let me just go back real quick. Remember we had up here, remember right here we said, oh look, some things are setting up printf, and we said, oh, here's something going into esi and edi. Does printf take arguments? It does. It takes a format string, it takes formatters, and then that's that. So you can pass in arguments via these registers. Kind of neat. Okay, so there's these registers. There's also more of them. We've got the stack pointer in here. We've got registers. Once they got past 8 original ones, they went, oh, let's just name them R8, R9, R10. They got lazy. They didn't want to keep naming them like fun names anymore. They just named them R8, R9, and R10. Yeah? So this is by bits 0 through 7 is 8 bits. 0 through 15 is 16 bits. 0 through 31 is 32 bits. And 0 through 63 is 64 bits. That's what that's all about. Okay? Because we start counting at 0 in computer science. Okay. So we've got all those registers in there, okay? And then we have some more. And we'll talk about the details of these in a little bit. Notice that the naming convention changes a little bit. It goes from RAX, EAX, AX, AL. And then when they get down to things like SI, it gets a little wacky. ESI is the same, SI is the same, and then like, well, SI and then SIL. It doesn't have just like SL. It's a little bit weird. So you always kind of got to remember that when you're looking at some of these. You go, what's SIL? I don't know what that is. Oh, you go back and look and go, oh, that's just SI's lowest 8 bits. Okay? And then with the numbers, it's changed too. It's like R8, R8D for double, R8W for word, R8B for byte. That's how the naming goes. Okay? All right. That's registers. We'll talk about how they're used in a minute. Question? Yeah, good question. What's the difference between caller and callee? Caller is the function that calls another function. Callee is the function that just got called. We'll clear that up in a couple of lectures, actually. Yeah. Yep.
What if you have like 10 arguments?
If you have 10 arguments, they go on the stack, as it turns out. So yeah, good question. If you have more than 7 arguments? Total 6 arguments. If you have more than 6 arguments, you start putting them on the stack. We'll learn how that works. And you can put as many as you want on the stack. Okay. You also, well, you can actually look and see how these are nested if you want. Okay, take a look at this program here. I won't go and run it right now. But if we have hello, and we say, let's print out RAX, you can print it using $. It's really too bad. It's called %RAX when you're using them, but then GDB makes you do $RAX. I hate that, but they do that. Whatever. If you print out, if you set RAX equal to this value, 4, 4, 5, 5, 6, 6, 7, 7, 8, 8, 9, 9, AA, BB, that's a 64-bit number. If you print out EAX, you only get the 32 bits. If you print out AX, you only get 16 bits. If you print out AL, you only get 1 byte or 8 bits. Okay, you can play around with that in GDB yourself. Okay. All right. Now, how do we actually use these registers? Okay, we're going to have to talk about accessing these registers and how we use them to relate back to memory. Okay, it all comes back down to the actual memory system that has an address. Remember, registers actually don't have an address. They have a name and they're in memory, but you can't address a register. It's a separate piece of memory than your regular big byte array. Okay? We've got a whole bunch of things up here called the operand forms. Okay? The operand forms just say, how am I going to access memory? Okay, and we're about to practice some of these, and I'll show you what these mean in a second. And this is, you got to get used to this, and you will. You will quickly get used to how this works. Okay? If we have constant values, okay, like 0 or like $1 is a constant value. It means 1. $0x1a means 0x1. It means 1a in hex. $-42 means -42 decimal. That's what we call an immediate value, which is a constant. Okay? So if you think immediate and constant, they really mean the same thing. Okay? We'll see why this, we'll practice these and see how they turn out in assembly language in a minute. I'm just setting it up. Okay? We also have register values, right? We have register values like %RAX, %EDX, %R8D. That's the ones on the back of this sheet. Okay? And then we have this block. And this block says, how do we access memory based on a couple of conditions? All right? I'll explain why we have so many different memory addressing forms in a few minutes. But basically it means there's lots of different ways to say, I want to access this piece of memory. Okay? We're going to go through those one by one. Well, not one by one. There's actually groups that we can talk about. The one on the bottom is actually the most generic version, which we'll spend a bit of time talking about. You can just know the bottom one, and you will be able to figure out all the rest. So that's nice. Okay? But these are just all a bunch of different ways you can access memory locations. We'll see why that's here's the most general one. Okay. Here's what's going on here. If you want to refer to a particular memory location, you can do it like this in the most general way. You can say, I have some number that I'm going to add. I know it looks like multiply, but it's going to add to some other number that is used like this. It goes RB, whatever that one is, plus S times Ri. That is a times in there. Okay, what are we doing? What the heck are we doing here? We are actually describing how to index into an array. You know how on the midterm you had to do that thing where you said char, star, and then you had the base plus I times the width? Doesn't that kind of look like a base plus some other value times like the ith value index? That's what's going on here, okay? The people who made this assembly language figured that we're going to be using arrays a lot, so let's build it into the lowest level of the program into how we access a particular part in memory. It's going to be super useful, and the compiler, like people who write compilers, love this addressing mode because it means you can easily access various memory locations just by this simple idea of saying I've got a base plus some index times a width, right? The S here is the width, basically, okay? Now, by the way, this is just kind of a side note, that S can only be 1, 2, 4, or 8. Turns out that's all they built into it. Why? Because you don't really have widths of 3 or 5 generally. Interesting that way. Okay, well, don't worry about that too much. I'll never ask you specifically about that. Right? We might see one later, but I won't ask you about that. Okay? All right. Let's actually practice this a little bit. So now finally we're going to see what this is like, what I'm actually driving towards here. Okay. Let's pretend we have a bunch of memories. I actually drew this up. I should have drawn this upside down like we normally do. But let's say this is address 100 and 104 and 108 and 10C. Okay? In address 100, we've got FF, 1 byte. In address 104, we've got AB, another byte. Okay? We might have other data in between those, but this is what we know so far. 108, we have a byte there, and 11, we have a byte at that location. We also have 3 registers that we care about. RAX holds the value 0x100. Guess what? It's a pointer in this case. Why? Because I said it was. And then it also relates to, we're going to say that it relates to that memory address there. Okay, RCX is just going to hold 1, and RDX is going to hold 3. Okay, so let's see how this memory stuff works. If I say %RAX, okay, if I say %RAX, that means, hang on, let me grab one thing out of my bag. That means that, oops, I don't actually have it in my bag. Okay, I won't grab that out of my bag. That means that we're going to look at the memory address that RAX points to. Okay? So in this case, the value of this, okay, oops, there we go, I'll do it this way, there we go, is, well, it's going to, if it's, I kind of misspoke in that case. In this case, the value of RAX is just 100. We're going to see it in a second where we actually access the value itself. Okay? If we have 0x104, okay, that is saying go to that memory location 104. Okay, 0x, and so what's at that location? What's at that location is AB. Okay, because we go to memory location 104 and we go, ah, there's 0xAB. Okay, all right. If we say $0x108, the dollar sign means it's a constant value. Okay, so we just care about it being the actual constant value. Okay, I'm just setting some things up for you. You're going to practice this in lots of different ways. You're going to see this a lot. Okay, if I put %RAX in parentheses, that actually means go to that location and figure it out. It's dereferencing is what it is. Okay, so %RAX is going to dereference to the value 0xFF. That's what the parentheses means in this case. For parentheses RAX. Remember how we had that most general form down here which said some immediate value and then 3 things inside here? Well, that's like saying 4 and then only 1 thing in here. What that means is add this value to this value, and that's the address that we're going to look in. Okay? So that's what we have. We have 4% RAX, means 4 away from RAX. RAX is 100. 4 away from that's 104. What's the value there? Oh, it's 0xAB. Okay. All right, let's look at the next one. Here's another one. Now we've expanded this a little bit. What it's saying is, let's do this. It's saying we've got an immediate, that's the 9. It's saying we've got an RB, that's RAX in this case, a base. And it's saying we have RDX, but it does not have this one. So what this is saying now is it's saying, OK, 9 plus RAX plus RDX. And what's the address there? Well, RAX is 100. RDX is 3, right? That's 103. 9 plus that's 112. 112 in hex, if you're adding all these hex up, is 10C. So we'd better get the value 0x11. That's a lot of stuff right there in one little thing. Now we get on to the big one. Well, no, we don't, actually. I thought that was the next one. No, we don't. We get into another similar one, right? Same thing here. Now we've got 260 plus whatever RCX is plus whatever RDX is. By the way, 260 in decimal is 104. So we got 104 plus 1, that's 105, plus 3 more is 106, 07, 08. What number should this be? 108, it should be 13. Okay. All right. Okay, here's a weird one. That is not a syntax error. It's actually just the way it goes. It's saying ignore this one. Right? So these last two means 4 times this one. So it's going to be 4 times RCX, which is 1. So that's going to be 4 plus FC. FC, FD, FE, FF, 100. I bet we're looking at that right there. Mind-blowing. Okay, is there one more on this one? There is one more. All right, what's this one? This is more almost the general form. It leaves off the, if there's nothing here, by the way, it means 1, if there's nothing there. Okay, so what this is it's going to be RAX plus 4 times RDX. That's what this means, 4 times RDX. So RDX is 3. 3 times 4 is 12. 12 plus RAX is 112. We already said 112 is 10C, which means that hopefully we're looking at 0x11. It's a lot of stuff. Now, why am I blasting you this right now? You're going to have to start like you doing this arithmetic on these things. It's not particularly hard. It's just different. And you got to just know this form. And from this form, we could have figured out any of these other ones, basically. Well, any one from this one down, we could have figured them out. Yeah? Well, the default when it's out front, oh yeah, sorry, you're right. I was thinking, you're right. Default is 0 out here, correct. Yes, sorry, I lied about that. The default in the other ones, when you're multiplying, the default for this one is 1. Yeah, sorry. Thank you. Good catch. All right. That was a lot of stuff right there. Let's talk about data movement for a few minutes. I will give you a break, by the way. This is a lot of stuff all at once. Okay? Copying data from one place to another, we've already seen that's really important. It happens all the time. Let's figure out how that works. x86 instruction set is what we call a complex instruction set, or a complex instruction set architecture, CISC. Other types of architectures are called RISC, RISC instruction set architectures. Okay? And there's a guy named John Hennessy. Anybody heard of him? Yeah, he was the president of Stanford, and he just became the president of Alphabet, which owns Google. So, or not president, the CEO, no, the what is it? President of the board, chairman of the board. Is that what it is? Yeah, he's in the CS department. I sat next to him at lunch a couple days ago. I said, "Congratulations on being, getting a big job at Alphabet." And he created the RISC instruction set. Okay, so yeah. So if you don't know, you're at the right place to study computer science. There you go. But he invented this, and it was made into lots of computers like ARM computers and so forth. And he's done pretty well for himself because of that invention. All right, not alone. He did it with other people, but he kind of spearheaded the whole idea. Okay, we're going to talk about data movement in complex instruction set architectures, which means that we've got to think about all these weird memory things that we just talked about. It's much easier on an ARM, like the phone. Your phone is something that was just easier because it doesn't have all these weird ones. But let's start in basic mode here. We're going to have a move instruction, MOV. The move instruction is going to, a lot of times you'll just see it as MOV, right? It doesn't tag on these extra little parts. It's better if you tag them on because it tells you more information. You can actually figure out what's happening without the B, W, L, or Q, but it's nice to have them there so you remember what's going on. But let me show you what I mean. MOVB means move 1 byte. MOVW means move a word. MOVL means move a 32-bit word. And MOVQ means move a 64-bit word or a quad word. We've also got this other one here which says move a big absolute value. We'll get to what that means in a second. Okay? So we're discussing the move instruction. We're showing how the move instruction actually works. It's on your sheet. Okay? The move instruction has a source and a destination, as we mentioned earlier. Okay? You can't move from a memory location into a memory location, like in main memory. It turns out that's a limitation of the way the hardware is built. Why that's the case, go take a EE class on architecture and you'll learn more about that. Okay, but it's a limitation. You can only move from between two registers. You can only move from memory to a register or from a register to memory, or you can move an immediate value into a register. You can't even move an immediate value, in other words, a constant, directly into memory. First, you got to go through a register. Wow. So it's kind of painful sometimes. Okay? But let's see some examples of this. Okay? Move L. Move L says move a 32-bit value from the source, that's the first thing, to the destination, that's the second thing. In other words, it's saying in this case, move this constant value, 0x4050, into EAX. Okay? Now, we got to talk about one minor detail here. When you're moving exactly like this into EAX or EBX or ECX, all the E ones, it moves those, it copies those values, and then it wipes out the rest of it, that 64-bit value. In other words, it copies the value, the 32 bits, and then wipes out the next. It's the only instruction that does that. All the other moves that are smaller than the whole 64 do not zero out the top. It's historical why that's the case. But we'll see how that happens a little bit later. Okay, let's just look at, I'm just bringing it up now because you'll see it again. All right, move W. We are moving a 16-bit value from the BP register to the SP register. 16 bits get copied from BP into SP. And it is copy. It's not really move, it's copy. Here we're moving the byte from this memory address, it's RDI plus RCX, from that memory address into the AL register. 1 byte, that's how it works. Okay? Move byte, this constant, into the memory pointed to by the stack pointer. It's interesting. Okay? Down here, we are moving 64 bits from RAX into the memory location -12 away from RBP. In other words, 12 values previous to where RBP is. Question?
These are just examples though, right? So you could,
These are just examples, yes.
you could use any of these instructions to perform any of these manipulations depending on where you want to move things. And you, the inputs, sorry, the difference is you give the different destinations and different sources to
Yeah, I think I get what you're saying. I mean, basically, we're just showing examples here. You can use these to do lots of different types of movements. But in this case, we're just saying, hey, look, if I was going to move 1 byte from this memory location into AL, that's how I would do it. So it's just an example of how to do it. Just showing you the basics. These are not like definitive things. There's lots of, this is just examples. Very good. Yeah.
What happens if you try to move an immediate value but don't actually have enough bytes to store the whole value?
What happens if you try to move an immediate value but don't have enough bytes? Well, you're not going to. Immediate values can only be up to, as it turns out, 32 bits, as it turns out.
What if like you change -17 to like -1 million?
Oh, that's a good question. Yeah, if you tried to change this to -1 million and you're only moving 1 byte, I think it would move the lowest order byte. I think that's what it would do. But that's kind of not, that's like extra like information. You're probably not going to do that too often. Okay, let's move on. There is one more instruction called move ABSQ, which is rarely used, but it means if you want to move a whole 64-bit value into a 64-bit register, you use that. That's because all the other ones we saw never allow you to move a whole 64 bits. They only allow immediates to be 32 bits. Again, why is that the case? Go take a computer architecture course or ask me after class. We'll talk about that. Okay, don't worry too much about that detail. Just know that this instruction exists. Couple more things before I'm going to let you take a couple-minute break. There are 2 move instructions that can copy smaller values into bigger values. There is one called, the one's called MOVZ, which says move a value and zero out all the other bits. So move a small value into a bigger register, if it's a register, and zero out those bits. We've already got that happening in the move for EAX. Okay? But this means, for instance, move from a byte into a word, and all the parts of the byte that are, all the upper parts of the word should be zeroed. That's all this means. Okay? You don't see this too often either, but occasionally you do. Okay? There isn't one for a 4-byte source to an 8-byte destination, because we've already built that in. Look, it's a syntax thing. Don't stress too much about those details. Most of the details are on the sheet right here. You're going to need to know. Take a break. 3 minutes.
Hi. I had a question. I was trying to do the lab on my own.
Yeah.
And I was trying to run like code.c to see like
Yeah.
how that thing, and it was telling me I didn't have access to it.
Did you clone it?
Yes. You know what I didn't do?
Make it? Yeah.
I
That's it.
applied to, I think the student you were telling me about.
Did
her
you
name's
email?
Danae.
Oh, yeah,
I
okay.
emailed her and I applied.
Danae. Danae?
Danae.
D-A-N-A-E. Oh, she's a grad student. Interesting.
Yes.
Okay, awesome. Oh, she's awesome.
Yeah,
You'll love her.
excited.
You'll love talking to her. Email her. Cool. Hey.
I had a question
Yeah.
about, I don't remember which slide it was, but it was something like you're showing like the types and like their suffixes.
Yeah.
And I was confused like why some of the types were different suffixes despite having the same amount of bytes. Like doubles are 8 bytes, but they have an L suffix. Which
Yes.
is a double word.
Right. Because L in assembly language means 4 bytes.
Okay.
Long, it means 4 bytes in assembly world.
But doubles are 8 bytes though.
In C world, they are, yes.
Oh, okay.
So if you have a double, right, or a double here, like this one, right, that you can see up there. You have this double, right?
Oh.
Double is 8 bytes, right? Okay. And it turns out it's an L and S. These are ones that L. Yeah. If what you mean is why is this an L?
Yeah.
Is that what you mean? Yeah. Because it's floating point, and they just did it that way. Because the original floating points were single precision and double precision. So yeah, it turns out it's never an issue because you can't use floating point values with integer values. Good question. If that's what you're talking about, yeah, that's the,
Yeah.
yeah.
Yeah. Because like.
That's the only one that should be weird, though.
Yeah,
Single person and
so,
double.
Yeah, I get like int is like 4 bytes, and
Yeah.
then it has an L. but
Yes,
then
yes, yes. Yeah, yeah, sorry. It's just because it's floating point. Good call. Hi. What's up? Yeah, what's up, Rena? Uh-huh. A constant is a number.
Oh, just a number.
Just a
Okay,
number.
So it's not a,
Right.
yeah.
Right.
There's so many numbers, so.
Yeah, but you use those and you put that number into a register, for instance.
Okay, so it's like a special case, right? Like it's immediate to register. Like why isn't that
Yeah.
just like moving from memory?
Oh no, because it just moves that number. Makes sure that that register has the number you give it. It's not moving from any memory location. It's just putting 6 into RAX. Yeah. It's just saying I'm going to set this RAX to 6. There's your immediate value. It doesn't take it from any particular memory. Okay, good. Yep. Okay, here we go. Okay. Let's keep going a little bit on some of this stuff. I showed you one type of moving and zeroing. There's another interesting one called move S, which sign extends the significant bit. What it means is, yes, according to assembly language, there's no signs at all. But what it does is it says, okay, look, we know that numbers in general are 2's complement, and we have negatives. So we will allow you to take a number. Let's give an example here. Let's say you had the number. Let's say you had the number 1, 0, 1, 0, 1, 0, 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 7, 8. Okay, and you were trying to move that into a 16-bit value. If you were using move S B 8-bit to L 16-bit, if you were using that, what it would do is it would look at this high bit and it would copy and then extend this over 1, 2, 3, 4, 5, 6, 7, 8. Instead of putting zeros there, it puts the topmost bit. So its sign extends it. If this instead had been 0, 0, 1, 0, 1, 0, 1, oops, 1, 0, right? Then if you had done this same instruction here, move SBL, it would have extended it by saying, oh, that bit's a 0, make all these 0. 3, 4, 5, 6, 7, 8. That's what's happening there. Okay? So this instruction, again, is rarely used except when you're doing certain arithmetic and you want to move values from smaller ones into bigger ones. Let's say you cast a number from an int to a, let's say it was int to a long. Right? In C, this instruction might get used. So go, oh, okay, you want to move it now. You want to move it into this other value. So now it's going to sign extend it for you because it happens to be a signed int to a signed long. Okay? That's all that's about. Okay. Let's practice move. I know I just showed you this, but let's practice it here. Okay? If I want to move from EAX into a memory location, %RSP, okay? E means extended, which is the 32-bit version. What am I going to have right here? What letter? We are going to have, remember the letters are, we've got what? We've got byte, we've got word, we've got long, and we've got Q for quad. Okay, the 1-byte ones are B, the 16-byte ones are W, 32 is L, and 64 is Q. So if we're moving one that is from a 32-bit register, which one do we use? L, right? See if I did it. Oh, there we go. Oops, doesn't, yeah, there we go, L. Okay, I don't want to do it that way. Okay, I don't want to show you all those beforehand. Okay, let's look at this one. If we're moving from memory into a DX, and you can look at your sheet to see where DX is on here. DX is the 16-bit version. So this, I'll just write them over here. This is the 8, 16, 32, 64. Which one do we want right here? W for the word one. How about this one? We're moving an immediate value into BL, which is the low one. What is that going to be? It's going to be the 8 byte, or it's going to be B, because it's moving a byte, 1 byte, into BL, B low. Okay, question?
Sorry, can you say one more time what that syntax means? You have percent and then the parentheses RAX as opposed to just percent RAX?
The percent parentheses RAX means it means dereference the location where RAX points to. That's what that means. So it's going from a memory location.
But didn't we say before that it would just be parentheses around percent RAX to do that?
Yeah, you know what? I believe that should not be a percent there. Yeah, I think the percent should be inside. Yeah, I think I just did that. That's good call. You guys are so quick. Okay, I purposely put these in here so you to test you. All right, so in this one, we're moving from some memory location. Don't worry about the details of what that is, but now we know how to calculate it if we want to. RSP plus 4 times RDX into DL. So DL is a 1 byte one. Which one do we use? B again. Okay, and then in this case, we're moving from a memory location into RAX. RAX is the 64-bit Q. And this one we're going to move from DX, which is the 16-bit version, into a memory location, which means we're going to have what? W. Did you see how we didn't need to have those? You don't need all those ones, but it makes it nice to have them so you can immediately see what they are. Yeah, Shaggy.
So in some examples, we're looking at the destination and
Yeah. In some examples, we're looking at the destination. In some examples, we're looking at the source because they have to agree with one of them. So in other words, if you look at this one down here, well, this is going to be it's in parentheses, it's always going to be R, by the way, because the memory locations have to be 64-bit, it turns out. But this one is going to be the difference one here. You go, oh, DX. It's got to be you've got to, in this case, move from a 16-bit word location. Okay. All right. Any other questions on that? Yeah, in the back. Yeah, this came up a little bit earlier. Is the reason the ordering is different? It's historical, number one. Number two, there's another way of looking at assembly language which all does flip them, which gets really hard to understand if you're used to one and you start looking at the other. But that's really, it's arbitrary. Yeah, question?
How does the assembly know to use move B and move W?
How does the assembly know to use me? Just like we figured it out. It does the same exact figuring. Like and it's a little more subtle than that. The compiler figures it out, and it just gives a number to the underlying processor, and the underlying processor says, oh, this number means I only move a byte. This number means I only move a word, etc. So it's all built into the underlying numbers. Question? Why do we have to zero out? Why aren't we? Generally, we aren't, and they just built it that way. They said, well, we're not going to zero it out all the time. The only time we're going to zero it out is when we have the EAX one, as it turns out. I know, it's kind of historical and hokey, and that's the way it goes. Okay, here's some that are broken. Now, there's some really, really tricky ones that I'm about to show you, and it would rely on you really understanding the back of this. So don't stress if you're like, you're like not playing fair with me on this one. But some of these we should be able to figure out. Okay? So if we want to move a byte from this byte into a memory location, what's wrong with this? I just mentioned it a second ago, and it's real, like you might not quite pick it up. Yeah, Hassan? It's because memory locations are 64 bits, which is 8 bytes, and you're absolutely right, but what does that mean is wrong with this part? It's got to be what? It's got to be RBX, right? Because you can't have parentheses EBX, it turns out. It's always, anytime you see the parentheses, you're always going to have an R's in there, not B's or not the E's and so forth. Okay, so that's, oops, okay. Move W, percent RAX, oh, no, this is, hang on, we're at the other one again, hang on. Determine the appropriate suffix, we're doing the one where it is the problem with it. Okay. Okay, move percent RAX into percent RSP. Move L, percent RAX, into percent RSP. What's wrong with this? We use what? We use, for R, what's wrong? What are we trying to do here? Moving along, which is 32. We're trying to move it from a 64-bit. You're not allowed to do that. Okay, that was not a tricky, like that's not a mean one. Yes, question? It is possible to move just the, oh, is it possible to move the most significant 4 bytes? No, you'd have to shift it first, then move it, or yeah, you'd have to figure that out first. Good question. Yep, you're not allowed, there's no instructions that move the top part without first moving it, shifting it. Yeah, good question. Okay. The one thing that you may be able to move into RH, but that's it, or AH, for instance, the high byte, but that's it. Okay, how about this one? Move W from a memory location into 4 plus some other memory location. What's wrong with that one? Yeah. You try and move memory to memory. Not allowed. Okay, whoops, not allowed to do that. Okay, how about this? AL to SL, this is a one that's like too tricky. You would have to look on here and go, SL, what is SL? Oh, there is no SL. Thanks for that, right? It's not AL to SL, it's SIL as it turns out. That one's SIL. Okay, how about this one? Percent RAX into the immediate value 0x123. Can't move into an immediate value, it doesn't make any sense. Right? I mean, it doesn't even do the address or anything, you can't do that. Okay? And then move L, EAX to DX. What's the problem with that one? Destination is 1 byte, but we're trying to move L. So we can't do that. We can't move a 16-bit value into an, wait, is that DX? Sorry, DX is a 16-bit. L is what? A 32-bit, yeah. So you can't do that. Okay? And then this one's another one. Let's see. Is there an SI? Let's see. There is an SI. Okay. What's wrong with this one? Move byte from SI. What's SI? It's a 16. Oh, that's another tricky one too. So that's another problem there. Okay, so let's see. Did we get these mostly right? There we go. Instruction, mismatch between instructions and register ID. So you won't often see these sorts of things because the compiler won't create them and you're not going to be writing your own. But you should definitely be able to read these, okay? We're not going to give you code that's like wrong like this generally because the compiler's not going to do it, and we're not going to make you do it. So I'm showing you this to kind of get your brain thinking about what's happening and how to read these, but we're probably not going to show you ones that are wrong. Like, what's the point? Because you're not going to be writing any of this code. Okay. Let's do a little bit, for the last few minutes, C to assembly. Okay? So let's take a look at a program here. Okay? We've actually got a program that is got a main function, and it's got some printfs in there, and it's got a function that we're going to call called exchange, which is up here. Okay? If you want to do this on your own, by the way, and analyze this, you can go to a web page called gcc.godbolt, it's a guy named Matthew Godbolt who runs it, .org. And you have to set it up this way, but you can type all this in and it will give you the assembly code for that, which is actually kind of neat. Okay? Let's see, let's actually do that right now. So let's go here and let's, oops, I did not mean to do that. Hold on, there we go. Okay, so let's do this. Let's actually copy all of this. I'm going to copy this. I'm going to go to this web page, and hopefully it'll come up, and I'll try to make it big enough so you can read it. Okay, all right. So we go up here and we say, okay, what are we using the right compiler? 5.4. I already did it, so it knows already. Are we using the right -OG? Yep, -STD. I didn't do -G, but we'll just leave it at that. And then you can go and paste your code in here, and it will. Did it paste okay? I don't know if it actually updated. Did it look like it updated? Yes, it did. It updated it. So now you can go look at the actual code in here. And you can go and you can start to see, oh, well, let's see what's going on. Let's see. Over here, we are doing, again, we're doing something with the stack pointer here. Oh, now we know how to move. Before you didn't know how to move, now we do. Move Q 1,000 into some location in memory, on the stack, as it turns out. Oh, that's kind of cool. All right, then it's going to move L. Actually, you know what? Yeah, this is right. And then it's going to move L42 into a register. Okay. Then it's going to move 1,000 again for some reason. Well, we'll find out. Maybe you have to look at this and see why that's the case a little bit later. Into the ESI register. On your sheet, what does it say ESI and EDI are? I mentioned this earlier. ESI is the second argument. EDI is the first argument. It just moved 42 into EDX, which ends up being 42 into EDX. And then it moved 1,000 into ESI. And then it's going to move this pointer value to EDI, which is the second. It's the first argument, okay? And then it's going to call printf. So all this was just to do call printf, so forth. You had a question? Yeah. It's moving the immediate value 1,000 into the location on the stack 8 away from RSP. That's what that's doing. It's moving the 64-bit value 1,000, moving along. Oh, and guess what? We're doing longs here. Yeah. This stuff is interesting because, like, the first time you see this, and remember, I'm not making you write any of this, I'm just making you read it. So it's like we're kind of learning a foreign language, not even just a programming language, right? We're learning, like, hey, how is this stuff done, right? And this is just the beginning, like day one of how this stuff is done, okay? So let's actually look down a little bit more here, okay? If we go down a little bit more, we've called printf right here. Then we're going to move 42 into ESI. ESI is the second argument. And then we are going to, this is another instruction we haven't learned. We'll learn that on Monday. It's another move instruction, but it's basically moving an address for us. It's doing like the ampersand is what this is doing. And it's moving that into RDI. Oh, well, look at that. RDI is the first instruction. Look what we have in exchange up here. A pointer to a long. And we have a long. This is RSI, and this is RDI. And didn't we just move, I'll tell you, we haven't learned this one yet, but this moves the address of that location into RDI, and this moves the value 42 into RDI. Oh, and I bet we're about to call the exchange function, okay? We call the exchange function right there. So again, I'm not expecting you guys to get this stuff right this minute. This is a whole bunch of stuff I threw at you on day one. By the end of next week, you will be able to read this stuff like nobody's business. Why? Because there's an assignment that's not next week, but the week after, called the binary bomb, which is all about reading assembly. It's this exact stuff that you'll have to be able to do. I'm looking at people going, I could never do that. You will get this stuff. It is, you read enough of this and you go, oh, I see how it is. Okay? I will see you guys Monday.